To perform mutation, I'm going to define another parameter named as mutation rate, and it is denoted by letter mu here, and it's equal to mu parameter. And let's define this in our first and main script as well. Params.mu will be, for example, 0.1 means 10%, and that means we're going to mutate and alter 10% of genes in average. It can be, for example, 2 of 10, 3 of 10 even, and 0 of 10. And in average, if we calculate the average value, it's equivalent to altering and modifying 1 gene out of 10 for now. And we have 10 variables here, and that will be almost 1 gene out of this nvar, 10 genes here. Okay, let's save this, and here we have the parameter mu, and we're going to perform mutation. But before we enter the loop for mutation, we have a matrix of empty individuals here, which has 2 columns. And the structure of 2-column matrix is not needed anymore. And we must convert this to a single column structure. To do this, we can convert popc to vertical matrix or single column matrix. To do this, we set popc equal to popc all elements. This notation always will convert any matrix to a single dimensional matrix known as a single column matrix. Okay, we have converted this, and now we can iterate on all members of this popc, and we can use the numel popc here, or nc. Simply the number of elements in popc is nc. You can use nc as well. And here we must perform mutation. To do so, I'm going to define another function which returns y, the mutated version, and a function named mutate, and it accepts x and another parameter mu. So we must know what's the value of mutation rate, and that's needed to perform mutation. So we're going to pass the value of mu from here, it's defined here, into this function. Here we have some binary variables in x, and we're going to change them by probability of mu in average. So what we can do, and we're going to create a random process actually. If you create a random number uniformly distributed in the range from 0 to 1, real numbers, then the output of this number will be always a real number from 0 to 1. And what's the probability? This random number is less than or equal to, for example, half. And you know that the probability of this expression to be true is equal to half. And you may set another number, for example alpha here, which is from 0 to 1, and it is true with probability of alpha. So for example, if you run this, in half of time, in average, this will be true. And to check this, let's create a 10 by 10 matrix of real random numbers in the range from 0 to 1, and let's compare them with half, and you'll get this. And if you check for the number of ones here and the number of zeros, then in average, according to the definition of our probability distribution, we have 50 ones and 50 zeros in average. And we can check for this. For example, let's define this as A, and let's calculate the sum of all elements in A, and that's 45. And let's calculate another one, 47. I'm going to run this in one line, in a single line. And if you run this, in average, you will get 50 ones and 50 zeros. And we are going to use this fact to determine where we must alter or modify the value of genes. And it can be determined using this expression. We have a flag, we can use the flag name, and that's equal to a random number generated in the range of 0 to 1, a set of random numbers uniformly distributed with the size of x, with the same size, and compare these values to mutation rate. And then we have ones with the probability of mu here. So this is a logical expression here. I'm going to put this inside parentheses. It's not needed, but for readability, I'm going to put them inside parentheses. And this is a logical expression, and it has 1 as elements with probability of mu. So we're going to set a new value for x when we have flag equal to 1. Firstly, we know that y is everywhere equal to x at the beginning of mutation. And then wherever the flag has true value, this is the logical indexing, then it will be equal to 1 minus x flag in the same positions, in the same indices, that this expression is true. This is called logical indexing in MATLAB, and we set all of members of y equal to x, and then we alter the values which are indicated by flag, and that's where we have this random number less than mu. And we know that this expression is true with the probability of mu. And that's it. This code means that we are going to alter, we're going to change a value inside our original chromosome with probability of mu. So we implemented the mutation mechanism here with these 3 lines of code. Okay, let's save this. Now we're ready to perform mutation on our popc, and we have popc l, the else element, dot position. We're going to change the position of this, and we're going to perform mutation on this. Mutate the same position with this mutation rate. So perform mutation. This is the original position. It passed to mutation function, and then it will change to this value, and then the position value will be replaced by this value, which is the return, the output variable of this function. So we're going to simply mutate popcl here. After this, we can evaluate this solution. So let's evaluate the solution here. popcl.cost value equals to cost function evaluated at the position of this member. I'm going to copy this here, and that's it. We evaluated the solution as well. And similar to this part, let's add some comment here too. I'm going to add generate random solution. I'm going to evaluate solution, and here we're going to compare solution to best solve ever found. And I'm going to copy this and have this here, and we have evaluation here. I'm going to compare this popcl with best, so we have popcl here, and we have here, we compare popcl.cost, and if it is less than or better than the best sol.cost, then popcl will replace best sol. It is determined as best sol. It has the best record ever found. Okay, we perform mutation, we evaluated the newly created solution, the mutant, and finally we compare to best solution ever found, and we update the best solution. And finally, here we can update best cost of iteration here, and we set the best cost of this very iteration equal to best sold dot cost, and that's the best solution we have found up to now. And we updated the best record we have here, and now we have a population. We have pop C here, and we're going to merge them. We're going to sort them according to the value of cost, and then we're going to select top members to create the population for the next generation. Okay, let's merge populations. We create the population equal to pop and merge it with pop C. You know that pop has n pop rows and one column. It's a single column matrix, and here we converted pop C to a single column matrix, so we must concatenate them in vertical order. And to do this, it can be done by this notation. We put pop here and pop C under that, or we can use simply semicolon here to have them in vertical order. What notation you wish, you can use here. It's a merged population, pop, and now we can sort this population according this new population according to the value of costs. For example, let's have breakpoint here. I'm going to have a breakpoint here, and I'm going to run this, and we have a population now, and we have pop 20 elements in this form, and if we want, we can gather the values of costs as this. We've seen this before, pop.cost, and that's the cost values of our population, and we can sort this, and you see that it sorts by default in the ascending order. So the lower values of costs are at the beginning of our sequence, our array, and the higher values of costs are at the end. And if we want, we can get the sort order which is used to sort to this array. Sort actually returns two values. One is the sorted array, sorted costs, and the other is the sort order. And this is the sorted costs values. It's same as this, and sort order. We know that the 9th element in the population has the lowest cost value. So let's check for the 9th element. Okay, it has 3 as cost value. And what about the pop 4? The 4th element has 4 as cost value. And what about 11? You can check for 11, and that has also 4 as cost value. And if you check, for example, pop 7 will have 8 ones, and it is the worst solution we have now. So we call sort function in this order, and we have sort order as second output. If you want, you can replace this notation with this. I'm going to use tilde here as first parameter, as first output. I'm going to tell MATLAB that I do not need this output, and it will return SO. It's the sort order of this array. And if I rearrange members of population with the sort order, then I'm going to sort the population, and that's it. We've done. We sorted the population according to values of costs. I'm going to change the population to pop, which is rearranged by sort order, and that's it. If we check for pop 1, we'll get the first member, the best, and pop end, the final member, as the worst member. And if we now, for example, have the values of costs here, we'll get this. And that's it. We have the cost values and it's sorted. So to sort population, I'm going to quit debugging mode here. And to sort population, we have this. We're going to check for sort order. So tilde, SO, and sort pop.cost. And we're going to rearrange members of pop with this sort order, and that's it. And finally, we have sorted version of population, our merged population, and we can convert this to a function if you want. For example, let's convert this to pop equal to sort population pop. We know that can be defined in this way. Sort order is the sort order of this pop.cost, and it will return the rearranged version of population with this sort order, and that's it. I created sort population function, and here I am calling this sort population function using this notation. And if you wish, what's the last value of pop? It's defined here. You can cut this and replace this with this and remove this part. So we have merge and sort populations. We merged populations here, and then we sorted this, and then we have a sorted and merged population. And now remove extra members, extra individuals from population, and we have pop equal to pop from first element up to n pop, and that's selecting this part only. We select this part of population and replace all of population, this variable, with this one. And at the end of this iteration, we have a new population, and when we return back here, we create another popc, we create new offsprings, we mutate them, we again merge them, and we select the best among them. We're going to remove extra individuals and then repeat this loop of evolution. And that's it. We implemented a genetic algorithm. And if you want, you can display some information about the process of algorithm and print some information on the screen to tell what's going on. So I'm going to display iteration information here. We have the disp command in MATLAB, and we can use several notations to format strings in MATLAB, but for MACWART compatibility, I'm going to use the character array instead of strings. Here we have iteration it. I know it is string, but we're going to replace this with its numerical value very soon. Iteration it, and best cost ever found equals to best cost of this iteration. Okay, and you know that these variables it and best cost it must be outside of this string. And now we have this, and this as 4 separate values, and we must glue them and we must have them together, and we use concatenation operators here. And this is a numerical value. We must to a string character array using num2str function, and also we must change this using num2str. This will convert our numeric type to string type, and that's it. This will type iteration, for example 1 best cost equal to this. Let's move this part here to make them closer, the definition and the usage part, and it's it. I think we finished the implementation of genetic algorithm, and now we're ready to run this algorithm. Okay, and we must run app1, because if you call this function directly, it will ask you to provide problem and params, and you don't know what's the value of them. And here we provided any necessary information for calling this function. And let's run this by hitting this button or hitting the F5 button, or simply let's clear this screen and typing app1. And that's it. You see that at iteration 1 we have a solution 1 in that. At the second iteration, GA was not successful to find new solution, but at the third iteration it found the solution, and the other iterations we can ignore those iterations, and we were able to stop the execution of algorithm right here at the end of iteration 3. But it's a simple program here, and I don't check for termination conditions. And the only termination condition applied here is the maximum number of iterations. Let's change the number of variables here to 100. And it's quite a hard problem to solve. And let's check what's the result. And you see, we started with 38 errors, actually 38 ones, and GA reduced it to 13. And it seems that GA is not able to solve the problem. We must give GA more time with giving it more iterations. Okay, let's run app1, and it reached 4. And also we can increase the number of iterations again. app1. No, it's not able to find the solution. Let's try increasing the number of population members, 100. And let's check for the result. It's not able to find the solution. And why? It relies in the structure of algorithm, the structure of operators we used. And the main reason is single point crossover. We must change this operator, or if we are sure about our operators, and for example, we implemented the uniform crossover and still we have problem, then we must tune the algorithm parameters, for example, mu and others. For now, for example, if we decrease the mutation rate here about 2% and check for the result, maybe we have some improvements, and we have, you see that the solution is found at the end of 57th iteration, and there is no need to have 1000 iterations at all. Let's rerun the algorithm as well, and that's it. The higher mutation rate increases the exploration ability of the algorithm, but in the same time, it can result in the slow convergence of the algorithm. We need to decrease the level of exploration as we go forward in generations of genetic algorithm. Here we started with small changes, small mutation rate, and it helped us. But it's not easy all the time, and we cannot use same strategy for all problems. Sometimes we must improve our operators, for example, crossover or even mutation. Especially now we're dealing with binary valued chromosomes. But in real valued chromosomes or some other structures for chromosomes, some sophisticated problems, we must design operators, crossover and mutation operators, to improve the quality of solutions. Here, with tuning a parameter, we have the desired solution. But you must take care of operators as well. And parameters are too important also. Okay, for now, we have implemented GA using single point crossover. In the following steps, we're going to implement other crossover operators. And remember, we are selecting our parents randomly. It's not a fair strategy. It's not wise. And after that, we are going to implement the roulette wheel selection to make the selection process of parents even better. Okay, that's enough for now. Okay, let's define the other crossover operators. We've implemented single point crossover here, and I'm going to define the double point crossover operator. The general structure is a function which returns two parameters, two variables, y1 and y2, and the name of the function is double point crossover, and it accepts two parents, positions of two parents, and that's the general structure of crossover operators. Similar to single point crossover, now we must select two cutting points, and let's define the number of variables in the position, and we must select two cutting points from 1 up to n var -1, similar to single point crossover, and obviously the two cutting points, they should not be equal. And we must use this same technique we used to select parents earlier in genetic algorithm. In this step, we created a random permutation and we used first two elements, and we don't have any repeated number in a sequence of random numbers of permutation, and we use that fact to create distinct random numbers. Okay, let's create a rand pair of this size, and let's use J1 as Q1 and J2 as Q2. But we need to ensure that J1 is less than J2. And to do this, we select the minimum value among Q1 and Q2 as J1, and we select the larger one among them as J2. So using two members of Q at the first and second position, we find the minimum among them, the one is less than the other one, to define the J1, the first cutting point, and the larger one for define second cutting point. Okay? You may also use this notation as well, 1 up to 2. It will work fine. But for readability, I'm going to use this notation. Okay? We define the number of variables and we selected the cutting points randomly. And here we're ready to form our offsprings. So for the middle part, y1 will use x2, and for left part and right part, y1 will use x1. So x1 from 1 up to j1, and x2 from j1 plus 1 up to j2, and x1 again from j2 plus 1 up to end is the first offspring. As we talked about the double point crossover here, we use this from x1, this from x2, and this from x1 again. We just swap middle parts. Let's copy this line and let's change y1 to y2, x1 to x2, and x2 to x1. So I'm going to change this, and it's obvious that we change this part, the middle part, and if we again change this, this will x1. You change this to x1, this will x1 from 1 to j1, j1 plus 1 to j2, j2 plus 1 up to end, and that's exactly x1. But we swapped these middle parts and we are forming our offspring in this way. And that's double point crossover. And if you want to call this, you can just say that you're going to use double point crossover. Okay, I'm going to call this and I'm going to run this, and we have this. It works in a similar way. However, we can define the uniform crossover in a similar way. It returns y1 and y2 as output, and we have uniform crossover here, and we have x1 and x2, and we have the definition of uniform crossover as this. We have a flag, and we can convert this process and we can describe it as an arithmetic operation. We're going to create a flag of exchanges, gene exchanges, and then we're going to use these equations to form our offsprings. So first we need some random numbers, 0 or 1, and for any position available in this vector or this vector, we need a single number. So we're going to create random integer numbers from 0 to 1 and with the same size of x1. This will return a vector with same size as x1, which contains only zeros and ones. You see, we didn't define any variables, for example nvar, which indicate the number of variables. We just use this size here. And finally, we can use the arithmetic equations there to perform the uniform crossover. But let's review the element-wise product in MATLAB. For example, let's have alpha A as this matrix 2, 3, and 4, and let's have x as 5, 6, and 7. If you want to multiply these row vectors, you cannot do this because the dimensions of matrices you're going to calculate the product of them, you're going to multiply them, are not matching. And we must have same rows in the second matrix as same number of columns in the first matrix. But if you want, you can multiply these two vectors element by element. You can perform element-wise multiplication. And to do this, you use this operator, the dot product, the dot times operator, which is element-wise product, element-wise multiplication. And that's multiplication of 2 by 5, 3 by 6, and 4 by 7. And that's 10, 18, and 28. Now, we're going to use this operator to perform uniform crossover. And we know that y1, all elements of y1, equal to alpha, this flag, times, but element-wise product, x1 plus 1 minus alpha, element-wise product, x2. And you see that if alpha in any position equals to 1, then y1 will be equal to x1 in that position. Because this is a vectorized expression, and we're going to calculate all members of y1, and we use all members of alpha, x1 and x2 at once. And that's a vectorized expression. Anywhere that alpha equals to 1, then y1 will be exactly equal to x1. And if alpha in any index is equal to 0, then y1 will be equal to x2. So let's copy this line of code, and we have y2 equal to alpha times x2 and 1 minus alpha times x1. And that's it. We performed uniform crossover in this way, and if you want, you can use uniform crossover in this way, and you can check for the result. And you see, maybe work better in this case, and in general, we have better performances from uniform crossover, but single point crossover and double point crossover have their own advantages as well. Okay, now I'm going to create a combination of these crossover operators as a practice, and I'm going to create a function which returns y1, y2 as crossover or random crossover or combined crossover, okay, or my crossover. Let's name this my crossover, and it will accept y1, x1 and x2, and we're going to select one of these operators randomly. And to do so, I'm going to select, for example, m as a random integer number from 1 up to 3, and I'm going to check for the value of m and use one of these functions to perform crossover. So let's switch for the values of m, and we know for the value 1 we're going to perform the single point crossover, and we have single point crossover for x1 and x2, and for case 2 I'm going to use this and just change single to double. And for other cases or otherwise, I'm going to use uniform crossover, and it's a randomized and stochastic combination of these 3 crossover functions. You can change the way you're selecting crossover operators to have different probabilities for these operators. And for example, if you implement the roulette wheel selection for GA, and we're going to implement in the next part of the video tutorial, if you have the implementation of roulette wheel selection, you can use that to perform 3 operations with different probabilities. And for now, for example, if you change this range to 5, then we will have 1, 2, 3, and 4 as output. And for 1, we have single point crossover. For 2, we have double point crossover. And for other values, and that's 3 and 4, we have uniform crossover. So the probability of single point crossover will be 25%. And for double point crossover will be 25%, and 50% will remain for uniform crossover. You can change this, or you can change the options you have here. But for now, I'm going to use same value of probability here, and I'm going to change uniform crossover to my crossover here, and you can check for the output here, and that's it. It used all of operators here. You can, if you wish, you can print the operator used, or you can count the number of operations used to have reports of how many times you're going to use single, double, or uniform. Okay, we implemented all crossover methods, and we combined 3 of them to create a stochastic combination of those methods. Now we're ready to change the way we are selecting parents. And for this video tutorial, I'm going to implement the roulette wheel selection. And we will do this in the next part.